My name is Vinny. I am the co-founder of Succeed Easy Tutorials. It's my pleasure to present to you today arithmetic operations with significant figures. As you know, arithmetic operations means addition, subtraction, multiplication, and division. So let's begin with addition or subtraction with significant figures. Let's look at addition involving significant figures. Say we want to measure the length of a block or a log of wood. Let's say we begin with L1 as one log and L2 as another log. So if we are able to measure the length of block, let's say L1, up to 2 decimal places, say if it is 14.57 meters, and for another log we measure the length only up to the 10th digit, that is 2.3 meters. In that case, if we were to add the two, if we were to stack the logs one above the other, what is going to be the total length? So if this is the kind of construction, one log over the other, one is 14.57 meter measured up to the 100th digit. See, and how many significant figures does it have? Obviously 4. And we want to add it to the other log's length, that is L2's length, which is 2.3 meter, which is measured up to the 10th digit. And incidentally, 2.3 means it has 2 significant figures. So what is going to be the total length? So if we measure it, if we add it arithmetically, obviously we are going to get 14.57 plus 02.30, totaling to 16.87 meters, right? In this case, if we take this as it is, then the issue is that this shows 16.87 shows that we have measured the entire measurement correct up to the 100th digit, isn't it? And this obviously has 4 significant figures. 1687 has 4 significant figures, right? So this gives us an incorrect representation of actually what we have really measured. Why? Because we have measured only one length out of the 2 correct up to the 100th digit. The other length has been measured only correct up to the 10th digit. So in that case, how do we proceed? In this case, we cannot go with the significant figures. Why? Because if you take the least of the 2, that is 2 significant figures, then in 168.87, this will be the 2 significant figures from the left will be only 1 and 6. That means 16. So you will have to, maybe you will round it to the units place, which should not be the case. Why? Because the accuracy here is right up to the 10th digit. So the way to go about this is that we must look at the data with the minimum accuracy, with 2.3 meters, which is correct up to the 10th place. Therefore, 16.87 meters, the total that we got from here, 16.87 meters, that needs to be rounded to the 10th digit, because the minimum accuracy was up to the 10th digit, isn't it? Now how do we round it? Now the normal rounding rule, see the digit which is next to 8, that is 7. 7 is greater than 5, and therefore we add 1 to 8, that is we round it up. So what do we get? We get 16.9 meters. This shows the correct level of accuracy of the data or of the joint log or block's length, right? Clear? Okay. And let's take another example. Suppose we measure a building. So if this length of the building is measured up to the nearest 10 feet as 270 feet, and if there is a tank over it which measures 16 feet, and this measurement of 16 feet is correct up to the nearest foot. In that case, if we total it, the total height is arithmetically it will be 270 plus 16, that is 286 feet, right? But that will be a wrong representation. Why? Because again, the same logic, that one data is correct up to the nearest 10 feet. There is only one more data which is correct up to the nearest foot. Now, when I say 286 feet, then the least accurate is nearest 10 feet, isn't it? That is the least accurate. So we need to consider the data that has the least accuracy among all the data that you add or subtract or whatever. If you do that kind of arithmetic operation, then you go with the least accuracy. Here the least accuracy is up to the nearest 10 feet. So we need to round it to the nearest 10 feet. And how do we round? We see that 6, the units place 6, it is greater than 5, and therefore we round it up. and 286 is the nearest rounding to 10 feet would be 290 feet. I hope I'm clear to you. Okay. Now, having seen addition and subtraction, let us take up multiplication or division with significant figures. Let's take up multiplication first. Let's take one example. Let's say we take area. Area, you know, is length into length, that is length square. It could be the area of a rectangle in terms of length and breadth. It will give us the area as L into B, right? It could be a square, A into A. A is one side of a square, so it will be A square. Or it could be any geometric figure. Let's say a simplest figure that comes to my mind is circle. So here if this is the radius and this is being the origin, if this is the radius, then the area would be given by pi r square, right? So the point here is that let's take one simplistic example. Let's take a rectangle which has length equal to 6.09 meters and breadth equals to 3.14 meters. Both of them incidentally have 3 significant digits. Okay. Now see what happens when we multiply. Okay. When we multiply to find the area, 6.09 meters into 3.14 meters, that gives us 19.1226 meters square, right? Now look at this. The measurement here was correct up to the 100th digit, isn't it? 100th digit. But here what we got in multiplication after multiplying is the 1000th digit and then even further, right? So the 10th, 100th, and then the 1000th digit we got, and then the 10,000th digit, right? So this is, if we consider this 19.1226 as the correct representation of the area, then we would be wrong, because we have taken more accuracy. We are considering more accuracy than there actually is in the data. So what we need to do, see here, the minimum significant digits in this and this data is 3, right? So what do? We take the minimum significant digits as 3, and in 19.1226, if you count from the left, see all of them are significant digits, isn't it? So from the left, the 3 significant digits will be 19 and then 0.1, isn't it? So other digits, we need to round them, isn't it? So we round the digits at this place. So 19.1, and since 2 is less than 5, so we keep 1 as it is. So we keep the data, we maintain the data value as it is, that is 19.1, and then we replace 226 by 000. All digits by 0 we replace, right? So what we get, 19.1 meters square. Am I clear to you? If you want to review, you can pause the video and have a deeper look at this. Okay. So please note, the accuracy that we took here was correct up to the last centimeter, or it was correct up to the last, it was correct up to the 100th of a meter, right? 09 is 100th of a meter, isn't it? Or it's the last centimeter. So we need, when we do the multiplication, we need to ensure that we don't take more accuracy than there actually is. So we go with the least significant digits among all the data which is available when we multiply. Clear? All right, let's proceed. Let's see division with significant figures. Okay, so in division, I've taken one arbitrary number, let's say 20.97245, which has 7 significant digits, isn't it? 1, 2, 3, 4, 5, 6, 7. We divide it, let's say, by another arbitrary number. I have taken 13.2, which has 3 significant digits. What you get from here is this number, 1.5888219, and then 69 gets repeated. It's a recurring number, 696969, it goes on. So if you divide this, then minimum of 7 and 3, that is, it is 3 minimum out of the given data. The minimum significant digits is 3. So consider 3 significant figures for the quotient. So this number, starting from the left, the 3 significant figures are 1, 5, and 8. So we need to round this at this third significant figure, this 8, which I marked with a red arrow. Now the following number is 8, marked with a blue arrow. 8 is greater than 5. So what do? Since 8 is greater than 5, we round it to, we add 1 to 8 to get 1.59, right? That becomes our final answer, considering significant figures, considering the right accuracy, right? Okay. Now here there is a word of caution. So let's say you take this number 7.256 multiplied by 3.2754 and then divide it by this 5.05, okay? So as to get this number 23.7663024 divided by 5.05. Now look, I have plotted the significant digits as you can see. So this has 4, this has 5, this has 3. Numerator has 9 significant digits and the denominator of right hand side is having 3 significant digits, isn't it? So the caution is that please do not round the numerator or the dividend, okay, to the minimum with 3 significant digits. That is, don't take 23.8 and then divide it by 5.05, as this may result in a loss of accuracy, okay? So that's the word of caution. So suggestion is that please take the entire number as it is till you reach the last stage. That is, take this number as it is and then find the quotient. So you get 4.70619 whatever, and then you take the minimum significant digits out of all the data that you operated on. The minimum being 3, you take 3 significant digits. So you round it to this, the third significant digit. So 6, the following number 6, which is marked with a blue arrow, 6 is greater than 5. So you round it up to get 4.71. You add 1 to 0 to get 4.71 as your final answer. Now you may actually see that even if you do 23.8 divided by 5.05, you may actually end up with 4.71. But trust me, that will not be a standard way to do problems, because here in this case the rounding has resulted and the numbers have played in such a manner as to give you the same result, but this may always not be the case. So please don't lose accuracy by rounding things way before than you should actually round them to. Okay, so don't round or don't lose accuracy, okay, till you get to the last point. I hope I'm clear to you, and I hope that this knowledge is going to be of some use to you. So please remember, always round the final value. So with that, we come to the end of this video. I hope you like the content, and if you do, please do subscribe, like and share. See you soon. Bye bye.